Let's record this one. Okay. All right. So Kale asked about 10-4. Let's take a look. So with the notation of the correspondence theorem, let H and H prime be corresponding subgroups. Prove that the index of H and G is the same as the index of H prime and G prime. Okay. So the way I think to do that is, so you said you had a notational question?
Or it's just, I don't know. I just don't know how to start. I don't know if it's just like, I don't know like the notation or like what it means by notation of correspondence theorem. I think I'm just not understanding what it's asking.
Well, let's look back at the correspondence theorem and just see if that helps. Should, hopefully. Here we go. So here's the correspondence theorem. And what do we have involved? We have a surjective homomorphism, an onto homomorphism. And I think the point that they're making there is, what did they use G prime?
Yeah, they used H and G prime.
So, okay, so that's a good question. So for this problem, they're going to be thinking that this is they're going to take G, script G, and write it as G prime.
Mm-hmm.
And they're going to take H, an element of here, namely a subgroup containing containing the kernel, and H prime is going to just be a subgroup of G prime.
Mm-hmm.
So that's the notation. That's what they're asking about. And they want you to show that the indices of these two subgroups are equal. So the way to do that is to just, the way I would think to do it is to go ahead and try to establish a bijection between the quotient sets, or the set of left cosets of these two guys. That's what I would try to do.
Okay.
And it may sound a little tricky, because what is the index? The index is the cardinality of the set of left cosets.
Yeah.
So just recall. So if I have a subgroup H, G, then G, index of H and G, this is equal to the cardinality of this quotient set. And that's, the set of left cosets.
Okay.
So now I have this surjective homomorphism. And I have an H prime. And so H and H prime correspond to each other, which if you look in the proof in the book or the one we gave in class means that phi of H equals H prime.
How do we know that?
So H, because this is a part of the correspondence theorem. So the correspondence theorem is saying, okay, so this is surjective. That's one thing. And the other thing is we have this, and okay, so let's call, I think it's better to recall the correspondence theorem. I'll just rewrite it here so I can work with it. So it says we have two sets. We have the set of subgroups of G containing H, it's containing the kernel. I'll just say kernel of phi. That's one set. And then we have just subgroups of G prime. G prime. So we have two sets. The correspondence theorem is basically saying that there is a natural bijection between them, a natural one-to-one correspondence between these two sets. And the way it works is if we have an element in here, namely a subgroup containing the kernel of phi of G, we send it to phi of H, this image under phi.
And then is phi of H implied that is in a subgroup of G prime?
It is a sub, it is. It is.
Okay.
And you prove that at some level. I think in one of the proofs about homomorphisms early on, you said if I have, it's one of the early exercises was if I take phi of G inverse, this equals phi of G inverse, right?
Oh, yeah.
So what that says is that, if I have something in here, then I have its inverse in here. And identity, and you also prove that phi of the identity is the identity. So the identity is in here, and then closure is also. So the image phi of H is a subgroup of G prime.
Okay.
It will be a subgroup. And then the reverse, the inverse of this map is you take H prime and you send it to all of the elements of G that are sent to H prime. So this is something we did in class. I'm not sure I did a good job explaining it, but it was something, the correspondence theorem.
Yeah, I think what's tripping me up is the correspondence theorem, because I remember we had that whole graph, and I think I just don't understand it. I think I just need to. I just don't know. I think that's.
So that's one of the reasons I was like trying to write this big table, is because I think it's helpful to kind of have more examples. And we can, maybe one thing we can do, let me explain this. Maybe what do I want to say? So see, the problem is the examples I've been giving in class, they're too small to really kind of show any interesting behavior. But you can indeed take this example here. And let me just show you at least what I mean from what I was talking about. And hopefully this will help. There was Matt asked a question, about cosets. And so hopefully, well, this isn't exactly about cosets, but we can also look at that. So here, this is the group S3, and you can identify just from looking at this table several subgroups, right? So you could look at 1, 1, 2, 1. That's a subgroup. 1, 1, 3 is a subgroup. All of the transpositions in 1, 2, 3. These are all subgroups. And the problem with this example is there's not this lattice thing that I was showing is not very interesting, because there's not any inclusions except the top one. There's all of S3, and then you have like 1, 1, 2, 3, 1, 3, 2. These are all the subgroups. And so the diagram that you would have would look something like this, and everything would go like this. And the idea is I draw a line if one is contained in the other. I connect to if one is contained with the other, just kind of going upward. And so the idea is that, if I had a surjective of correspondence theorem, if I had a surjective homomorphism from some group G to S3, then I could identify all the subgroups that contain the kernel of phi. And if I wrote them all down, it would look just like this picture, except they would be subgroups of G instead of these guys.
And so then, okay, so that makes more sense. So then you had a second tree like that. So is that what the correspondence theorem is saying? Is that
that's the other side? Yeah, exactly. This whole picture here is basically a picture of this. Each little guy in here is an element of that set, right? Each one of these is an element, right? Okay. Each of these is a subgroup of G prime, in this case S3. So I look at all of the subgroups of S3, and the picture I draw also says I've got these containments, one is contained in the other. And so I can kind of get this kind of nice picture of inclusions and all of this, what's called lattice of subgroups. I get this whole thing in here. And then the point is there's a mystery with some other group G, but I've got a homomorphism onto S3, and I can draw this picture of subgroups inside of G. It looks exactly the same, and it's all of the subgroups that contain the kernel. That's it.
So then does that imply that every subgroup of G has a corresponding subgroup that contains a kernel, or is it?
No, it doesn't imply that. That's too strong. So it's sort of relative to the kernel. There may be subgroups that don't contain the kernel. I mean, there may be many of them, and they're not as detected from this diagram, because to some extent you're quotienting out by the kernel when you look at this map. So if I'm just looking at this lattice over here, if I have a subgroup, for example, of the kernel, maybe the kernel is really interesting. It has a lot of interesting behavior and structure and stuff, but I'm completely lost all of that because phi has killed it. It sent everything to 1 in the kernel. So any kind of interesting things going on with the kernel, I don't see in this picture at all, or in the correspondence theorem. It's just things that sort of contain the kernel that I see.
Okay. So then what does it say? Like, I don't know. That's a dumb question, but like what does the correspondence theorem, like how can we apply it to other things? I think that's where I'm getting caught up on this problem.
Well, in large part, correspondence theorem you should think of as like almost a corollary of the first isomorphism theorem. And the point about, in the sense that what the first isomorphism theorem, which we covered today, says is that if I have one of these surjective homomorphisms, then in fact S3 is isomorphic as a group to G mod the kernel of phi. And so the point is that this correspondence is a manifestation of this isomorphism. It's saying that any kind of subgroup of S3 can be thought of as a subgroup of G mod its kernel, but all of the subgroups of G mod of the kernel can be thought of as, can be built from G and from those subgroups and the kernel. So I'm trying to answer your question by saying there's this other theorem that really tells us why this thing is true. And then what are the applications of the first isomorphism theorem? Well, the main application is to try to come to grips and understand what groups are, and to try to come up with a structure theorem, classification type theorem. And the idea, okay, so the idea is exactly what I was trying to say in class today, which is, okay, so groups are everywhere. So there has to be a certain point where people can acknowledge, and I'm not just talking to you, but those that watch at home, right? Like the groups are actually everywhere. All of these matrices groups, these change of coordinates groups, they're everywhere. Groups find themselves in, symmetries of all kinds of physical systems and modeled systems. And so if you apply the group and you kind of eliminate the symmetries or understand the symmetries, you can greatly simplify whatever model you're working with. So groups are everywhere. And so if we acknowledge that we're interested in groups, okay, and we would like to understand them, then the main step from there is to try to classify them. And so, for example, if you have a system with finite symmetries, you're interested in finite groups. So one of the many applications of first isomorphism would be to say, okay, I'm interested in classifying finite groups. How do I do that? Well, I can, and this is what I was saying in class today, I can talk about sort of atoms. I can talk about like the most fundamental, most sort of indecomposable groups that it may exist ever. And what are those? And I'll just tell you and whoever's watching what they are. So there's a notion of a simple group. It's a group with no non-trivial normal subgroups. Subgroups. So why would this be such an interesting thing? And the reason is because of the first isomorphism theorem. Let's say I have a complicated group G, and I find some nice proper normal subgroup N, and let's say everything is finite. Okay. So then all this, and I'm interested in classifying. So let's say I've classified all of the groups. I know every single group that exists up to order 100. Okay, and G is order 1,000, but N is order, I don't know, n is order, let's say 50, or I don't know, what is, yeah, sure, 50. Let's say n is order 50. So n is order 50, g is order 1,000, and I know everything up to order 100. So then I look at the quotient group, right? Because today we said we can actually form this group. This has order g over n. So in the example I'm looking at, this will have order 20, right? So I know what this group is. I classified all the groups up to order 100. So I know what this group is. And because n is order 50, I know what n is. And in fact, what I can do is I can sort of assemble G. I can understand G by appropriately putting together n and g over n. So I understand these two kind of more basic groups, smaller groups, and I can assemble the larger one.
Okay.
This is kind of this is what I mean by atoms, is like you can kind of, these are these simple groups, these are the ones that you can't do this with. And they're sort of the basic fundamental structures that everything else can be built from, like the molecules or whatever.
And you can like, so once you have the simple group, you could use that to construct the larger groups. Like
you have to know a few things. I mean, it's not so simple. It's not an immediate obvious thing. And but in some sense, those larger things do break down. There's a lot of this, all of the structure, I want to say all of the structure can be found from understanding these simple groups.
So they kind of like basis vectors, or are they something different? Like where you can get everything else by.
In a way, that's right.
So.
In a way, that's right. In fact, there is sort of a shadow of this, which would say, which may even be able to precisely make meaning of that. But yeah, in a way, that's right. So this is what the correspondence theorem is kind of circling around, these ideas, is saying, okay, well, I don't know about this group G, but I know about G, G prime, because it's smaller. It's a, image of G, and I know all kinds of stuff there, and I can bring all of that and learn things about G. So that's my best answer. But to the problem, I'm sure a lot of people are like, please stop talking and pressing fast forward on YouTube or something. But to the problem, let me just say, okay, so how would you go about solving this problem something? Okay, I've forgotten the problem. So it's the indices. Yes, okay, I remember.
Yeah.
The indices.
Yes.
So for that, I would say, okay, so what do we know? We know that H prime is equal to phi of H. That's what I was saying. This is the correspondence theorem. This is what and again, just look in the proof of the correspondence theorem. It'll be in there. But you should write some words about, okay, recall this is true. Okay, so this is the problem. So recall. Okay, so now define following map. G over H to G prime over H prime. And let's give it a name. I'll call it psi. And what is psi? I need to define it. So by psi of AH is equal to phi of A H prime. I mean, in some way, I shouldn't call it psi. Well, I'll call it psi. I don't know. I guess what I want to say is this is also equal to phi of AH. Parenthetically, we can see that's equal to phi of H.
Okay.
Recall, phi is this map from G in the correspondence theorem. Of course, they have a script G on the right, but okay. Phi is this map. Okay. Sorry, this is getting a little sloppy here. Let me just clean it up a little. Okay, so all this, where this is in. Okay, so now we're going to define this map this way. So first of all, is this well defined? Yes, it's certainly well defined because H prime equals phi of H and because it's a homomorphism, right? You can see that this is equal to this because, you know, this is equal to phi of A, phi of H, but phi of H is H prime. So this is well defined. Okay, so now we want to show that this is a bijection, right? To show that these have the same cardinality. So to show psi is a bijection. And okay, well, the first thing, let's do, I kind of am against trying to show and find an inverse in this case. I'd rather just show it's 1-to-1 onto. So let's just say, let's do onto first, surjective. So why is it surjective? Well, we have to remember about the correspondence theorem. Phi is surjective. So since phi is surjective, if BH prime is in G prime over H prime, there is an A in G, phi of A equaling B. All right, it's surjectivity. So then, but then by definition, we have that psi of A H, this is equal to phi of B A H prime, this is equal to B of H prime.
Okay.
So it's on to. So let's see what about 1-to-1. 1-to-1 or injective. Okay, so let's suppose that we have we have AH, we'll call them A1H, phi of A, oops. I mean, okay, I'll use psi, but maybe you could just use phi, I don't know. Psi of A1H equals psi of A2H.
Other files corrected. My bad. So,
Then phi of A1 H prime equals phi of A2 H prime. Which means, and I'm talking to those interested in cosets, and what we did today, two cosets are equal, two left cosets are equal if and only if, you know, the two representatives we have, the inverse of one times the other is in that subgroup. So we did this today, we used that today, and I'm pretty sure we proved it earlier. And if people don't remember that, they should check the book, but this is true. So this is true in G prime, if and only if, I mean, it's true we're in the group G prime, so I'm just saying, if and only if, oops, not the inverse, pardon me. We have this condition, right?
Yeah.
But that's true if and only if we can, because phi is a homomorphism, we have phi of A2 inverse A1 is an element of H prime.
Mhm.
And by definition, that's true if and only if A2 inverse A1 is an element of phi inverse of H prime. That's the definition of the inverse image of a subgroup. But this is equal to H.
Yeah.
In the correspondence. So A2 inverse A1 is an element of H, and then by the reverse reasoning, we have that their cosets are equal. And that's what we wanted to conclude. For injectivity, we want to say, okay, if psi sends the same elements to the same thing, or the two elements of the same thing, then those two elements were equal, and they are.
Okay, and then since they're equal, there can't be duplicates, and it's injective. Is that done?
Yeah, done. Injectivity is done, and then bijectivity is, I mean, bijection, we've established as a bijection, so we're done.
Okay. And that's just the question? That's all we have to do?
All we have to do, because the index is by definition the cardinality of the quotient set, of the set of left cosets. That's the definition of the index. So we've shown that these two set of left cosets, they have the same, there's a bijection between them, so they must have the same index. They must have the same cardinality.
Okay, that was way easier than I thought it was.
Always is, right? Well, maybe not always, but often. Actually, I think algebra is much more like that than other subjects. Is, you know, once you get it with algebra, it's like, oh my gosh, this is silly. You know, why have I struggled so much?
Yeah, I think it was just the whole correspondence theorem, and I didn't really know how to pull out the indices.
Yeah, like yeah. So I would say with that one, as with many of these kinds of questions, the first thing to do is to go and check the definitions. Make sure that you're understanding the definition of index first. Once you understand that it's related to those left cosets, you can say, okay, well, how do I define a map from one set of left cosets to the others? And then you just kind of have to follow what's in front of you. You know, there's not much choice as to how to proceed.
Yeah. That's all the questions I really had. Like, I just haven't done 11.5 yet, but I don't, that doesn't look awful. I think I could. So that's all I have, I think.
That sounds great. You can log off and that's fine. I'm just going to say a couple of things. I mean, if you want, you can say about like left cosets in general. I think I said it in class, but, and this is more to Matt. He had asked a question about it, but the idea, I'm just going to draw a picture here and just say, okay, you know, if you look at like a subgroup, for instance, of S3, like 1, 3, this is a nice subgroup, and you can find the left cosets by just multiplying this and seeing where it goes. Okay, so if you do that, you know, if you multiply by 1, you know, you'll get 1, 1, 3. If you multiply by 1, 3, you'll get this. You can then multiply by 1, 2, and you get 1, 2, 1, 3, 2. And you can also multiply by 1, 3, 2, and you'll get this, the same. Uh-oh. That's not good. Oh, I didn't do the right thing. I multiplied by 1, 2, 3. That would have been bad. Okay, good. Let me go back. So I need 1, 3, 2. There we go. We get the same thing. Or we can multiply by 2, 3 and get this. And I guess, so I'm coloring them because I want to emphasize that you're going to partition up the entire thing. So if I just look at the top column, or it's the top row, pardon me, you know, you can see you get this partition, right? 1, 2, 3, 1, 2, 3. I guess I can just look at this row. This row is an identical row. So if I look at this row, this is all the elements in S3. And I partition those elements up into 3 colors. And those 3 colors are the 3 different left cosets of this subgroup. So if we forget about what I just did, and I just kind of were to use the sad notation of of just cycling, you know, permutations and so on. I have this subgroup 1, 1, 3. It's a subgroup of S3. And now we can see, let's look at some of the invariants. H, this equals 2, right? It has 2 elements. S3, of course, has 6 elements. And we know Lagrange's theorem. Lagrange's theorem says that S3, the number of elements should equal the number of elements in H times the index of H in S3. I think I always switched. Yeah, I did it right. Okay, it's amazing. Let me switch the order here. Okay, but so what we see here is that in this particular case, right, we have 6 is equal to 2 times 3. So the index has to be 3. And as I said just a moment ago in this exercise, the index is the cardinality of the set of left cosets. And we see we have the 3 colors here. So that's the number of left cosets I have here, is I have 3. And if I want to write those down, of course, we can write down S3 over H. Okay, and it's a partition. So the elements of this are sets, are cosets. So they're not like elements of S3, they're actually sets. And we can write them down. So this one was 1, 1, 2, 1, 3, 2 was another. And 2, 3, 1, 2, 3 was this guy around here. 1, 2, 3. This was the last one. So this was so we color coded. We've got this one and this one and this guy. So these were the 3. And so we see this is a partition of S3. It is a partition. And we also see that these, if I want to write them in the notation we've been using in class, well, this of course is H. I can say this is 1, 2 times H. And I can say this is 2, 3 times H. But the thing about it is that, I keep on talking, when we're proving some of these theorems, I'm saying there's some ambiguity, right? And the point is that this is also 1, 3, 2 H. So this element in front is not unique, right? In fact, you can choose anything in the left coset as a representative. We call it a choice of representatives. So you choose something once you want to write it this way. But there's a lot of different things you can choose and you'll get the same left coset. It'll permute everything around if you made a different choice, but it stays within that left coset. So there is that ambiguity, but you can write it in these different ways. You'll also note that what we did today doesn't hold here, right? I cannot multiply these, right? If I take, for example, if I take 1, 3 and I multiply, well, I think I did this in class, but maybe, I don't know, maybe it's worth doing. Let's say if I take H, well, and I multiply 1, 2 H. Well, this is the set of all of the elements that I can make this way, by taking an element here, multiplying this, and then an element here. And so you'll see, you'll get 1, 2, you get 1, 3, 2. You get the elements in this because you can multiply just using the identity here. And then if you didn't use the identity, you would get 1, 3 times 1, 2. So that's 1, 2, 3. And I don't know what else you get. You get something else. But the point is that this has too many elements already to be a left coset. So I can't actually multiply these guys and stay within this. And that's because this is not normal. Whenever I say that, it's kind of like, what I mean is, it's not a normal subgroup. This is not a normal subgroup. If I conjugate 1, 3, for example, by 1, 2, I get 2, 3. So if that conjugation takes this and takes you out of this set into some other permutations. So you don't have this nice quotient group structure here. If we had chosen instead the group of one of these 3 elements, then we would get a normal subgroup, the alternating group, and the quotient would be isomorphic to like 1 minus 1 or Z mod 2. So that, I just wanted to add that in because Matt had asked about left cosets. I hope that helped clarify things a little bit. But yeah, so good problem session. Thanks for coming, Kale. I'll see you guys, or see you next week.
Okay. See ya. Thank you.
Yep.